Hey everybody, this is Larry. This is me doing a day 8 of the 8th of the November Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, and also, what would I say? Oh yeah. I guess with the daylight saving, this is now at 7 p.m. So, I don't know. I guess it's still the same time that I'm doing it every day, but it's just a little bit awkward. So we'll see how that goes. I don't know if that means anything. Might not, probably doesn't change anything. But anyway, I am solving these live, so let's get to it. Today's problem is unique binary search trees. So yeah, without really looking at this, there are a couple of ways to kind of think about this. One is that, just to be honest, this is a very, I wouldn't say very common, but common enough series, which is called the Catalan series. Catalan numbers or Catalan series? Catalan? And with that, there are a number of ways to kind of implement this. And it's only 19, so it doesn't really matter which way you do it. So we'll do it the divide and conquer way, I would guess. Mostly because it's easier to, I don't know if it's easy, but it's easier to prove. Though I mean, don't know it off my head, because in theory, the thing about this is that if you know this series, you just Google it and then you're gonna, figure that out. But that said, there is a kind of an O of n way of solving this with factorials and stuff like that, though technically O of n might not be accurate only in the sense that factorial it's not, the operations are not necessarily cheap unless you do some kind of modular math or something like that. Then it'll be quote unquote O of n, where n is the number and not the input size. But yeah. So there is a quote unquote cheaper way of doing it, but the way that I like to think about this, at least from scratch, is through that divide and conquer. And the way that we think about it is just kind of like a brute force kind of way, right? Let's think about naming these things always a little bit hard, but count of x, right? So what does count of x means? And we might not even need this helper method, but I always like to do it just so that it has good abstraction, maybe, but I don't know if that's true. But it makes it easier to make modification or like adapt to new code if necessary without changing the interface, right? So in theory, as an abstraction, that's better. But yeah, okay. So we can think about it. So okay, if x is equal to 1, we have one node, so we return 1. Technically, maybe if x is equal to 0, we also return 1 because there's one way to represent 0. I guess we can also rewrite this as 0 or 1. Though, I don't know, we shouldn't get any negative numbers, right? Okay. And then after that, we go, okay, so let's say we have X nodes, right? Well, the way that I would think about it is, okay, now let's say you have this node in the root, right? And then now you can say, and then you can brute force essentially how many nodes are on the left and how many nodes are on the right. So let's go for left is in range of from 0, and I know that starts from 0, but I just want to be more explicit, especially for this one, to x minus, I guess because we have to consume one node, so yeah, so that's going to be the case, and in this case, the number of nodes on the right side then would have to be x minus 1 minus left, right? 1 for the current node that you're, the root node. And then now we're just brute forcing how many ways there are there to count left and how many ways are there to count right. And now, so then we have some total is equal to 0, say. And then now we add, so number of ways to count left. And of course, the number of ways to count left and the number of ways to count right are independent of each other. So, excuse me. I'm doing this live, so it's a bit awkward. Because these are independent, we can multiply them, right? Because if there are 2 ways to do on the left and 3 ways to do on the right, then you just have some combination of them. And then at the very end, we just return total and that should be good. So now we return, and yeah, I mean, if you're a student, you'll notice that I didn't do any memorization, so it might be slow. How that went away. Okay, so that looks good. Also note that for small excuse me, for small inputs, and this is 19, I would actually try or 19. Because why not? And also the other thing that you can do is, of course, if you feel like this is too slow, you can take the answer in the brute force way and then, you know, just cache them or whatever. And as you can see, this is actually a little bit slow. So the way that we can think about this then, and for example, maybe I go, oh, I forgot this is too slow because this is definitely exponential and that it, you know, branches to the left, branches to the right. The thing to take advantage is, of course, that this is repeated subproblems, right? For every input that we have in here, we get the same output, right? So in that way, we can just store what we call memorization, which means that we store the same thing, so that for future use, because that doesn't change no matter what, as long as the input's the same. So maybe we could go, let's just say cache is equal to none times n plus 1, so that we can store from 0 to n. That's why you have n plus 1. And then hash cache is equal to 4. Oh, why is it a two-dimensional matrix? Sorry, friends. But same thing. And then now we can go, okay, if has cache of x, we return cache of x. Otherwise, we set the hash cache to true. And of course, cache of x is equal to total. And then that should speed it up really quickly. And we'll go over the analysis in a second. And of course, I think one thing that I feel like I don't do well enough, to be honest, on my videos is that I don't really go over, so I kind of do these things backwards a little bit from how I actually do it in real life in a contest situation, to be honest, even though it might not look it. Because the first thing I would do, to be honest, is I would go, okay, I have this algorithm, and let's say I have memorization. Is it fast enough? So only after that do I start implementing, because otherwise, why would you implement something that you know is too slow, right? That said, I think this way is a little bit better for you for learning. So let me know what you think. So x could go from 0 to n, inclusive, and then that's it, right? So for each input, each input takes O of n times because we have an O of n loop, and each of these n loops does O of one cost. So each input takes O of n time, and of course each input takes O of one space, and in total we have O of n time, O of one space. That's pretty much all I have. Oh, sorry. Wow, I lied. I'm so used to, I saw this one and this one, but I actually lined them up a little bit differently, this particular part. Sorry. So this is O of n, this is O of n. So each input takes O of n time. So this is going to be n squared time, and this is O of n space. Wow. I don't know what I'm thinking. That's pretty much all I have for this one. Let me know what you think. Like I said, there is a factorial way of doing it. I don't know if that is easy to explain, that particular one. This one, you can see that I actually don't memorize the thing, even though I do know the first 4 or 5 series of the sequence, so that I do recognize if it comes up 1, 2, 5, 14, 42. Actually, I should remember 132 as well. But that said, actually this is coming from first scratch or from like first principles. So let me know what you think. That's all I have. Hit the like button and the subscribe button. Join me on Discord. Let me take a quick look at see what I did a year ago. Okay, so I did actually mostly the same a year ago. So yeah, pretty much the same actually. Anyway, stay good, stay healthy, to good mental health. I'll see you later, and let me know what you think. Bye bye.